Okay, this next topic deals with the vector form of what we talked about yesterday, which was speed and distance. So today we're going to be dealing with velocity, which means it's going to contain the speed within it, but we have to give it the context as to the direction in which it's traveling. For example, a car travels 65 miles per hour is a description of speed. A car travels 65 miles per hour due north is a description of velocity. It's added the direction to it. The formula for velocity is essentially the same with one huge difference. V equals d over t, but the d means displacement instead of total distance traveled. And this is where people get into some difficulties. The displacement is the distance from the starting point of the object's travels. Whenever an object moves linearly, the displacement and the total distance are identical, meaning that the speed and velocity are identical as well. That does happen. However, if the object travels 500 meters north and 500 meters east, the displacement and the total distance traveled now are two different values. The total distance is 1,000 meters, but the distance from the beginning point of the trip is determined by using the Pythagorean Theorem. So let's take a look at that. So, we're going 500, We're going 500 kilometers north. Here's our starting point right here, 500 kilometers north, and 500 kilometers east. Now, actually I probably should put this up here because it goes, say go north first, and then it's going to go east 500 here. And the results from the beginning point to the end point right there. Now this is not very well drawn because I mean this is 500 way less than this 500 here. But whatever, you get the idea. And what's happening here is that this is the displacement. So this is going to be the hypotenuse of this right triangle right here. So we use the Pythagorean Theorem. So d equals the square root of 500 squared plus 500 squared. And that turns out to 707 meters. Or kilometers, or whatever. Kilometers. Okay? But now we gotta know what this angle is right here. Well, if it's going to equal distance north and east, then we say that this is northeast. That's the direction. Now that only happens when it's evenly divided between the two measurements. In other words, I could say that this is 45 degrees north of east, because here's east and another 45 degrees north of that. Or I could say it's 45 degrees east of north, which means to go from here to here. But we don't call it either way because they mean the same thing, so we just say northeast. Now let's suppose that the answer was 30 degrees north of east, which means it's going to be, that would be like right here. And let's say it could have been expressed as 6 degrees east of north. Could be represented either way. Well, this falls under the heading of eating peas with a knife. It can be done, but it shouldn't be. So what we do instead is we pick the vector quantity that is less than 45 degrees. Okay? So we would say 30 degrees north and east if that were to be the answer. It's not for this problem. But if it were, that's the one that we're going to use. So always use a value in your angle or your direction that is less than 45 degrees. Because if it's more than 45 degrees, it's actually closer to the other direction. So you have to flip them around, like we did here. East and north becomes north and east. Okay? If the trip took 1 minute and 20 seconds, we want that velocity in meters per second, which is the SI unit for velocity, so meters per second. If they never ask you for a specific label, then they are, the default mode will be the meter per second. And so in this case, oh, well here it says meters, so I guess I can't read. Yeah, this is meters, whatever. So let's say 707 meters divided by 80 seconds, if it took 1 minute and 20 seconds to go, so the answer is 8.84 meters per second. So, thank you. The 150-year-old man can't read. All right, so let's take a look at problem 7b, page 60 now. 7b was that train problem we did yesterday, in which we dealt with the scalar version of it. And that's when it went 300 kilometers one direction, 300 kilometers the other direction, so travel a total of 600 kilometers. So let's take a look at that problem from a vector point of view. So you got the train going in this direction here. Kilometers, and I'm 100% sure it is kilometers. The train would travel 300 meters. Probably wouldn't be that long. We'll probably be even longer than the trip. And goes back another 300 kilometers. Where has it ended up? At the very beginning. So what is this displacement? 0 kilometers. So what's its velocity? Yeah, 0 meters per second. 4.136 figs, 0.00. Okay? Now, let's take a look at problem 11b. And as is the case with most physics problems, we generally like to use diagrams to help us understand what the problem is really asking, what the context is and all that. So 11b, this one on 11b. We want the net displacement. Okay? So what is the net displacement? Well, actually what we're going to do is we're going to do more than just the net displacement. We are going to find the net displacement, but we're also going to find the direction based upon what it says. It doesn't ask for it, but you know, I like to do things more than what is asked of me sometimes. So let's take a look at this. What do we got going on here? We got 40 meters north and 20 meters west. Okay? 40 meters north, 20 meters west. So again, draw my directional axes. So I'm going to go 40 meters north. 20 meters west, and that means that the displacement is from the beginning point to the opposite side of this parallelogram / rectangle that is created here. We're going to do that a lot. So you might want to get in the habit of drawing rectangles every time you do these vector things. Now, if you take a look at this, you can notice that this angle right here is closer to the north direction than it is to the east direction. So when we get down to the displacement, that's the one we're going to pick on to solve. But the displacement, which is this distance right here, which I'll call C for the Pythagorean Theorem, is going to be C equals the square root of 20 squared plus 40 squared. And I don't remember offhand what I have here, so take a quick look. About 44.7 meters. Okay. .7 meters. So that displacement is going to be that much. Now, next question is, where do we end up in relation to where we started? What is my angle here? So this is where trigonometry comes in. Yes, we're going to use a lot of trigonometry in this class. A lot of trigonometry. So don't forget your SOHCAHTOA. Sine, opposite, hypotenuse, cosine, adjacent, hypotenuse, and tangent, opposite, over adjacent. So in this triangle right here, this right triangle, here's the right angle right there. That's your hypotenuse, the C. So that means that this is the adjacent to the angle, and that is opposite to the angle. So the only one that uses both adjacent and opposite is TOA. I TOA you so. So tangent of theta, mathematicians love to use this Greek letter theta. I don't know why, because theta doesn't even have an A. I would think alpha would work, this angle begins with alpha. And I think angle is a word the Greeks use too, so this doesn't make any sense. But I digress yet again. Opposite, which is 20 meters, over adjacent, which is 40 meters. And I'm going to want this in degrees. We'll have lots of fun with gradients later on. So make sure your calculator is in the mode of degree. It won't have an effect upon the calculation for anything else, but for angles, it's really important. So since we already know what the tangent is, we're trying to figure out what this angle is, then we're going to have to find the inverse tangent, or what they call the arc tangent, of the fraction 20 meters over 40 meters. And we know, because this is closer to north than it is to west, this is going to be some number of degrees west of north. So we type that into our calculator with the second tangent function, 20 over 40, or just say 0.5 because that's half, whatever. And your answer turns out to be 26.6 degrees. So that's going to be 26.6 degrees west of north. Your assignment, problems 8B, 10, and 12 on page 60.